So in this section, we're going to go over some advancements and pitfalls in the recommender system industry. In particular, we're going to go over Google DeepMind Team's slate Markov decision process and one of their data generalization algorithms. We're also going to go into some hardware they developed called Tensor processing units that are especially designed for deep neural networks. And then we're going to give an overview of IBM Watson, and we're going to go into one of their recommender systems that they applied to healthcare and the bad publicity they've gotten recently from it, and how that might not necessarily have been their fault. One of Google's recommender algorithms currently being applied to YouTube is based off of the Markov decision process called slate MDP. A Markov decision process is a process that starts in a state and is given a set of actions. When an actor chooses one of the actions, the process moves to a new state. This new state is completely independent of all prior states and actions. When this process is applied to a recommender system, the actor becomes the user. When a user chooses one of the recommendations, the recommender algorithm records the data and is given a reward. In this way, the recommender algorithm trains itself to provide better recommendations for the user. So here's a screenshot from my homepage on youtube.com. There's a whole bunch of recommended videos for me to watch, and all these recommended videos together would form the slate in a slate Markov decision process. Clearly from the videos, I am a superhero nerd that watches kung fu bloopers, studies machine learning, and might watch Jimmy Kimmel sometimes. Of course, slate MDP is just the tip of the iceberg for Google. Google currently has several different billion user services that utilize recommender systems. When you start taking a look at how big Google is, you start to realize the most amazing thing about the recommender systems is how they handle all that data. One of the ways Google handles all this data is through use of their tensor processing units, which is a piece of hardware especially designed for deep neural networks. There are several improvements over traditional CPUs and GPUs. If you take a look at the block diagram there on the right, 24% of the board is devoted to the matrix multiply unit, which on a TPU is 2D. On CPUs and GPUs, it's a whole bunch of smaller 1D matrices. 2D matrices are better suited for purposes in deep neural networks. Along with that, TPUs only use 8-bit integers over 32-bit or greater. It's easy to see why there would be faster data manipulation and less energy consumption along with that. And then the use of 2D matrices allows use of systolic arrays, which are arrays that can perform calculations on the data within the array. And this cuts down on the amount of times the processor has to access the register. So there were a couple of things I wanted to show you before moving on from tensor processing units. One is the increase in energy efficiency of a TPU over a traditional CPU. Here's a depiction of the energy it takes for the CPU to calculate one single addition of an integer, 70 picojoules, and for a TPU it was less than 1, which is kind of amazing. On this graph, it's kind of hard to understand without any context, but the blue line is the TPU, and this is basically their inference speeds. TPUs experience 15 to 30 times increase over traditional methods. Basically, it's the amount of time it takes for them to make decisions. Also amazing. So another way Google handles all the data is through use of something called a Wolpertinger architecture, which is a tough word to say, but it's basically an algorithm that works well with large action sets. Prior information about actions is leveraged to embed the actions into a continuous space from which action sets are generalized. What I'm saying there is the discrete data given to the algorithm is graphed basically in a continuous graph, and from that graph the algorithm chooses the next action set. After that, an approximate nearest neighbor approach is utilized to find the next discrete action. So this is going from now continuous data back to discrete, and it can be a generalized decision any one of the actions in the action set is chosen, or the highest valued action within the set relative to the cost function. The use of this architecture allows finding discrete actions in logarithmic time, and Google is continuing the research on this architecture because it's so promising. So now that we've discussed some of the cool things happening with Google, we can start discussing some of the things happening with IBM Watson, which aren't all good. IBM Watson is taking a different approach than Google, where Google is kind of self-applying its AI in areas that they think it's needed. IBM Watson is taking a service-oriented approach. Users don't need to be experts in the field to use Watson. They can just be someone with an experiment or some study data to parse. Watson has three coverage areas: explore, predict, and assemble. Explore tries to find patterns within the data. Predict tries to predict outcomes of the data, and assemble kind of depicts these findings in graphs and infographics. IBM Watson has won several awards, including Design and Electric's Innovator of the Year Award for 2017, and regardless of the current publicity coming out about Watson, it is one of the leaders in the field. That's not to say that IBM didn't self-apply its AI to areas they thought it would have a big impact. They did, and one of the biggest ones was the healthcare industry. They even made their own division called IBM Watson Health, and it was the flagship application of IBM Watson. Specifically within the healthcare industry, they were purporting that IBM Watson was going to be able to analyze data of cancer patients and recommend appropriate treatment. However, there have been claims that IBM Watson was giving incorrect recommendations. While the claims made against IBM Watson were true, its shortcomings were not the result of IBM Watson being an inferior AI system. In fact, the problems experienced by IBM Watson in the healthcare industry would have been experienced by any AI system. For example, the healthcare industry is notorious for being slow at adopting new technologies, and this includes data collection methods. As such, IBM Watson was lacking sufficient data for training. On top of that, healthcare is very complex. People go to school for 7 years to become doctors, and expecting an AI system to come in and make the same level of recommendations as doctors is a little overzealous on such a short time period. Combine these factors with IBM's marketing team and their gross over-exaggeration of Watson's abilities to date, and you get some bad publicity out of it. The current state of AI in the healthcare industry is IBM Watson is still leading. Experts believe that AI will have major impact on the healthcare industry, and that the problems experienced by IBM Watson could have happened to any machine learning or recommender algorithm. In fact, at the end of the day, IBM Watson is a great AI system, and it will still probably be IBM Watson that leads the charge into healthcare.